So today, as I have mentioned already, we will continue with response of LTI systems to complex exponentials. Well, as you may remember very well that the signal e to the power st is an eigenfunction to LTI system. So if e to the power st is at the input, at the output you have e to the power st times some eigenvalue, and this eigenvalue is nothing but this h of s here, integral from minus infinity to plus infinity, e to the power minus st ht dt is the eigenvalue. So if s has a general form alpha plus j omega, then we have this relationship. You have e to the power st, e to the power st at the input of an, let's say, LTI system, and at the output you have e to the power st times the eigenvalue, which is integral from minus infinity to plus infinity, e to the power minus st h of t dt, and this is actually e to the power st times h of s. So this is the output of an LTI system if you have e to the power st at the input, and this h of s is the eigenvalue, this is the eigenfunction. So if s is purely imaginary, let's say in the form of j omega, then we have nothing changing. So we have e to the power j omega t at the input of my LTI system, and at the output again I have e to the power j omega t times h of omega. Okay, so h of omega is actually nothing but the signal with s equals j omega. So here I have an example. Let x1t is cosine pi over 4t and x2t is cosine 3 pi over 4t, and they are at the input separately of an LTI system, and I have the h of omega frequency, the impulse response in frequency domain is given as rect omega over pi. So what are the outputs y1 and y2? Actually, let's write x1 of t. It is cosine pi over 4t, and it is equal to, you know very well that e to the power j pi over 4t plus e to the power minus j pi over 4t over 2. And of course, if you use the above, let's say, observation, y1 of t is nothing but 1 over 2 e to the power j pi over 4t times rect of pi over 4 1 over pi. So I have done nothing but here, instead of omega, I have put pi over 4 first for the first term, plus e to the power minus j pi over 4t rectangle of minus pi over 4 times 1 over pi. So now I have put it here minus pi over 4 instead of omega. So I'm just using this relation, nothing more. So e to the power, so I have the first term, I have the second term. Instead of omega, now I have pi over 4 in the first term and minus pi over 4 in the second term, where h of omega is rectangle of omega over pi. So that's it. If you go and evaluate some terms, this is equal to 1 over 2 e to the power j pi over 4t times rect of 1 over 4 plus e to the power minus j pi over 4t and rect of minus 1 over 4. Do you remember rect t? What was rect t? It was in between plus minus 1 over 2, it was 1. Remember rect t? So in 1 over 4 and minus 1 over 4, rect t is, of course, 1. So this is equal to 1 over 2 e to the power j pi over 4t plus e to the power minus j pi over 4t and it's equal to the input cosine pi over 4t is y of t, y1 of t at t up. So this is y1 of t. So y2 of t is your homework. Please try this at home and be sure that you can solve this by yourself. So actually the manipulations are quite easy, but you know they need some familiarity with the algebra, but it is quite easy to evaluate. So we have, as the second section, we have Fourier transform of periodic signals. Well, remember that we have seen that periodic signals, if they represent some properties, they can be written in the form of Fourier series coefficients, and this was the Fourier series expansion. Well, now we will see that if impulses are allowed in the transform x of omega, in this case you can represent periodic signals in Fourier domain as well. And in this way, actually, Fourier transform is an asset that you can use to represent both periodic and aperiodic signals. So this is some powerful idea. So let's start with considering a single, let's say, impulsive term. Let's consider 2 pi impulse omega minus omega 0. So if I start with this x of omega, so what is x of t in this case? Well, I'm using very well synthesis equation, integral from minus infinity to plus infinity, 2 pi impulse omega minus omega 0 e to the power j omega t d omega. So this is x of t. So this is x of omega. So they cancel out, and by using the very well-known shifting property, this is nothing but e to the power j omega 0 t. So I have concluded that Fourier transform of e to the power j omega 0 t is nothing but 2 pi impulse omega minus omega 0. So this is my, let's say, Fourier transform pair. Well, if in general I write such an x of omega, so k from minus infinity to plus infinity, 2 pi a k impulse omega minus k omega 0. So let's start with such a relationship. So in this case, my x of t is nothing but 1 over 2 pi integral from minus infinity to plus infinity x of omega e to the power j omega t d omega. And this is 1 over 2 pi integral from minus infinity to plus infinity k 2 pi a k impulse omega minus k omega 0 e to the power j omega t d omega. So this is my x of t. Of course, as usual, 2 pi's cancel out. Since integration and summations are linear operators, I can switch their positions. A k integral from minus infinity to plus infinity impulse omega minus k omega 0 e to the power j omega t d omega, and this is equal to integral from k minus infinity to plus infinity a k e to the power j k omega 0 t. But of course, what I have done, I've used the shifting property. This integral is nothing but e to the power jk omega 0 t. So it's here, and I have the rest, summation and ak. So what is this? Of course, you know that this is Fourier series expansion for periodic x of t. So if x of t is periodic and represented with Fourier series coefficients ak, then I can easily find its Fourier transform by using this relationship. So in summary, first determine the Fourier series coefficients of ak, then write the Fourier transform x of omega as summation 2 pi ak impulse omega minus k omega 0. So that's it. So it is as in here. So I have a simple example. First, I will find the Fourier series coefficients ak. X of t is equal to 1 over 2 e to the power j omega 0 t plus e to the power minus j omega 0 t. And this is my Fourier series expansion, e to the power j k omega 0 t. And in the second step, I will write x of omega directly. It is k 2 pi ak impulse omega minus k omega 0, and it is equal to 2 pi a1 impulse omega minus omega 0 plus 2 pi a minus 1 impulse omega plus omega 0, and this is finally equal to pi times impulse omega minus omega 0 plus pi times impulse omega plus omega 0. So x of omega is this. This is my omega, this is plus omega 0, this is minus omega 0, and this is pi is the area under those impulses. So quite easy, just some, manipulations. Well, my next example is the sine wave. Again, I'll start with writing x of t by using Euler's relation. So this is 2j e to the power j omega 0 t plus minus 1 over 2j e to the power minus j omega 0 t. This is, of course, a1. This is, of course, a minus 1. So x of omega is simply pi over j impulse omega minus omega 0 minus pi over j impulse omega plus omega 0. So if you go and plot j times x of omega at omega 0, you have pi. At minus omega 0, you have minus pi. By the way, these are the areas under impulses. So this impulse goes to infinity, this impulse goes to minus infinity, but the area under those impulses are plus minus pi as given in the figure. Well, next I have the periodic square wave. So it is somehow tedious to show, but we have calculated the Fourier series coefficients of periodic square wave as this. This is, remember, omega 0 t1 over pi sinc k omega 0 t1 over pi. So this was the Fourier series coefficients. Well, if you go with the second step, again, x of omega is summation k from minus infinity to plus infinity, 2 pi ak impulse omega minus k omega 0. This is equal to summation k 2 pi omega 0 t1 over pi sinc k omega 0 t1 over pi times impulse omega minus k omega 0. So this is my x of omega. So if I go and evaluate some terms, I have summation k2 omega 0 t1 sinc k omega 0 t1 over pi impulse omega minus k omega 0. Well, if you assume t0 is 4t1, so just to make some calculations easy. So if I do this, omega 0 is 2 pi over t0, and this is equal to 2 pi over 4t1, which is actually pi over 2t1. Then omega 0 t1 is nothing but pi over 2. So what I have is summation k pi times sinc k over 2 impulse omega minus k omega 0. So this is the Fourier transform for my periodic square wave. I know that sinc is 0, whenever the inside of parentheses is let's say integer. So this is 0 for k equals 2, k equals 4, and etc. So first, let me draw the envelope for x of omega. So this is my envelope. So for k equals 2, it means that I have 2 omega 0 here. For k equals minus 2, it means I have minus 2 omega 0 here. The sinc is 0. So this is the envelope. So this is 4 omega 0. This is minus 4 omega 0. And in between, I have my impulses. So there is an impulse here. There's an impulse here. There's an impulse here. There's an impulse there. An impulse there. So this is omega 0. This is minus omega 0. This is 3 omega 0. This is minus 3 omega 0. So at k equals 0, I know that sinc is 1. So the area of this very first impulse is nothing but pi here. And the others are scaled by the, of course, the areas are scaled by the impulse. So this is the case. So this is my Fourier transform for the periodic square wave. It is an impulse train. So this is, of course, an impulse train, but it is scaled by pi times sinc. So this is the envelope here. Well, next example is periodic impulse train. So x of t is summation k from minus infinity to plus infinity impulse t minus kt. So if you look what x of t looks like it is this, of course. So this is t. So it goes on like this. They all have the same amplitude, although it is not in my drawing. So this is t, this is 0, this is minus t, this is 2t, this is 3t, minus 2t, minus 3t, and it goes on like this. So what about ak in the first step? It is 1 over 2 integral from minus t over 2 to t over 2, impulse of t, e to the power minus j, k, omega 0 t, dt. And this is, of course, 1 over t. And in the second step, x of omega is summation k from minus infinity to plus infinity, 2 pi over t, impulse omega minus k omega 0. So it is my impulse train. 0, omega 0, 2, omega 0, 3, omega 0, minus omega 0, minus 2, omega 0, and it goes on like this. So this is my impulse train. And of course, they all have the same amplitude, not amplitude, but the area, let's say, of 2 pi over t. So this is my impulse train. So the impulse train, periodic impulse train, has the Fourier transform, which is also a periodic impulse train. And of course, omega 0 is nothing but 2 pi over t. Well, the next thing that we will discuss is the properties of Fourier transform. First, I will talk about some notations. So I have the signal on the right-hand side, and I have the Fourier transform on the right-hand side. I have x of t in the left-hand side. I have x of omega in the right-hand side. And Fourier transform can be shown with this as well. So, or the inverse Fourier transform can be shown by f inverse. So it means that x of omega is the Fourier transform of x of t, and x of t is obtained by inverse Fourier transform of x of omega. if I have more than one signal, I have x of t, x of omega, y of t, y of omega. So quite simple. And also we will compare the properties with those of Fourier series expansion. So I have x tilde of t, which has Fourier series coefficients ak, and I have y tilde of t, which is periodic, of course, with Fourier series coefficients of bk. Well, note that those x of t's, y of t's need not be periodic, so they do not need to be, they do not need to be periodic, so they can be aperiodic signals as well. But those x tilde t's and y tilde t's are periodic signals. Also remember, once more, you can find Fourier transform for periodic signals and aperiodic signals, but Fourier series expansion is valid for periodic signals. Okay, so this is the case. Well, the first property is the linearity property. Linearity property is simple. So if you have ax of t plus byt at the inputs, if you find the Fourier transform for the signal, you have ax omega and by omega as the Fourier transform. So let's prove this. I have axt plus byt. This is simply integral axt plus byt e to power minus j omega t dt. I can separate the integral into two. A times integral xt e to power minus j omega t dt plus b times integral y of t e to power minus j omega t dt. So of course this is x of omega, this is of course y of omega. So in the end I have a times x omega plus b times y omega. So this is the Fourier transform of axt plus byt. So linearity tells you this. Well, you can simplify this. If you have only axt at the input, of course you have ax omega at the output. And this is, remember, homogeneity property. So scaling, if you scale a signal, the Fourier transform is also scaled. Well, if I have periodic x of t, x tilde of t, and y tilde of t, if I sum them, again, the Fourier series coefficients are summed, and the resultant signal has the same period of x tilde t and y tilde t. Well, if x tilde t and y tilde t do not have the same period, remember, the resultant signal has the period of least common multiple of both periods. So this is the case for periodic signals. Time shift. Time shift is simple. If you shift a signal in time, it is multiplied with a complex exponential in frequency. So again, the proof is simple. I have x of t minus t0. This is integral x of t minus t0 e to the power minus j omega t dt. If you have a change of variables, let's say if you call t minus t0 as tau, it means that dt is d tau and t is nothing but tau plus t0. So if you continue, this is integral x of tau e to the power minus j omega tau plus t0 instead of t. So I have d tau here, and this is equal to e to the power minus j omega t0 integral from minus infinity to plus infinity x of tau e to the power minus j omega tau d tau. Well, this is nothing but x of omega. So the result is e to the power minus j omega t0 times x of omega. So this is my time shift property. So if you shift in time, it's multiplied with complex exponential in frequency. You can, as you can remember, this was also similar in Fourier series discussions. If you shift a periodic signal, then it is the Fourier series coefficient is multiplied with the complex exponential. So this was the similar idea. Well, what else? Time and frequency scaling. If you scale the time, frequency is also scaled accordingly. So what is this? If you have Fourier transform of x of at, this is nothing but integral from minus infinity to plus infinity x of at e power minus j omega t dt. So this is equals, if you have at equals tau change of variables, this is equal to integral from minus infinity to plus infinity x of tau e power minus j omega over a tau d tau over a, if a is a positive number. Otherwise, the integration changes limits x of tau e power minus j omega over a d tau over a if a is a negative number. So this always happens if you change variables and if the signs are changing, the integral also changes limits. So if a is positive, I have from minus infinity to plus infinity. If a is negative, I have from infinity to plus infinity. But I can put here a minus, and a plus here. So if you do this, actually the result does not change. So what does it tell you? If a is negative, there is a minus here. If a is positive, there is a plus here. So it is simple. This is equal to, so if you come from here, this is equal to 1 over absolute a integral from minus infinity to plus infinity x of tau e to the power minus j omega over a tau d tau, and this is nothing but 1 over absolute a x of omega over a. So that's it. Simple. Well, this property, of course, tells you that time and frequency parameters are scaled inversely. So if one expands, the other contracts, and vice versa. If you remember the Fourier series coefficients for this case, x tilde at is periodic with t0 over a, and x tilde at has Fourier series coefficients ak. So if you compare xt and x tilde t, what is this? Let's write here. X tilde of t is periodic with t0, so it is summation k ak e to the power j k 2 pi over t0 t. So this is the Fourier series expansion for x tilde t. What about x tilde of at? Let's write it here. It is equal to summation k with the same Fourier series coefficients, but with different period jk 2 pi over t0 over a times t. So t0 over a is the period of x tilde at. Although the coefficients are the same here, the representations are of course different since the periods are different for those signals. Well, I have an example. I have x of minus t, and it has Fourier transform x of minus omega. That's simple. So if you use this formula, a equals minus 1. So absolute minus 1 is of course 1. So I only have x of omega over minus 1, which is x of minus omega here. Next example shows you to use some properties together to find the Fourier transform for x of t. So I have this interesting signal. So it is 1 in the interval 1 to 2. It is 1.5 in the integral in the limit in the interval from 2 to 3, and it is again 1 in the interval from 3 to 4, and it is 0 elsewhere. So this x of t is the combination of some rectangular pulses. First one is rect t. Let me draw here rect t. So this is my rect t. This is 1, this is 1 over 2, this is minus 1 over 2. And I have rect t over 3. So rect t over 3 is, let me draw in a better way. So rect t over 3, let me draw it here. So it is non-zero from minus 3 over 2 to 3 over 2. So you can check this by this. So this rect t, remember rect t, it was non-zero from t in the interval minus 1 over 2 to plus 1 over 2. So what about rect t over 3? If I put here t over 3, then this 3 can come here and come there. So rect t over 3 is non-zero from minus 3 over 2 up to 3 over 2. So this is my rect t, and this is 1. Well, x of t is nothing but 1 over 2. So let's call this as x1, this as x2. It is nothing but 1 over 2 x1 of t minus 5 over 2 plus x2 of t minus 5 over 2. And this is nothing but 1 over 2 rect t minus 5 over 2 plus rect t over 3 minus 5 over 2. So this is my x of t, which is represented as a linear combination of rectangular signals. Well, first remember that, let's write x1 t, which is rect t. It has Fourier transform sinc omega over 2 pi, and x2t is rect t over 3, and with, of course, a is 1 over 3 in this example, and it is nothing but has Fourier transform 3 sinc 3 omega over 2 pi. So this is the Fourier transform for x2t. So if I write the final answer, this is nothing but 1 over 2. I am using linearity and time shift properties, e to the power minus j 5 over 2 omega times sinc omega over 2 pi plus 3 times e to the power j minus j 5 over 2 omega times sinc 3 omega over 2 pi. So this is the Fourier transform for x of t, which is obtained using scaling and shifting properties. Next property is conjugation and conjugate symmetry. If x of t has Fourier transform x of omega, x conjugate t has Fourier transform x conjugate of minus omega. So this is again easy to prove. Let's start with writing Fourier transform of x conjugate of t. This is integral from minus plus infinity x conjugate of t e to the power minus j omega t dt, and this equals to integral from minus plus infinity x of t e to the power j omega t dt with a conjugate. So I have done nothing but I have put this conjugate to the outside. But of course, there is this e to the power minus omega t. I should also take its conjugate as well. So the conjugate of this one is nothing but this plus term. So I have x of t e to the power j omega t dt in the integral. Well, if you compare this one and the ordinary Fourier transform, what is it? They are the same, except that there is a minus sign here. So it is x of minus omega with a conjugate at the outside. Well, this is simple. If x of t is real, it means that it and its conjugates are equal. Then in this case, I have that x of t is equal to x conjugate of t, and Fourier transform of x of t is of course equal to Fourier transform of x conjugate of t, and it tells me that x of omega is equal to x conjugate of minus omega. So this is my case for a real signal. Well, what does this tell you? X of omega is equal to x conjugate of minus omega. So if x of omega is equal to x conjugate of minus omega, then if I take conjugate of both sides, x conjugate of omega is equal to x of minus omega. So if you take the conjugate of both sides, x conjugate of omega is equal to x of minus omega. Well, it tells you that real part of x of omega is equal to real part of x of minus omega, and the imaginary parts are similar but with a minus sign. So how can you show this? So if x of omega is equal to x conjugate of minus omega, or if x conjugate of omega is equal to x of minus omega, then I will write that, let's say, x of omega has the form a of omega plus jb omega. So let's assume that x of omega has such a form. So what about x conjugate of minus omega? X conjugate of minus omega is nothing but, instead of omega I will put minus omega, so this is a of minus omega. For conjugation I should inverse this, negate this, minus j b of minus omega. So it tells me that both are equal. So if those two are equal, then it means that a of omega is equal to a of minus omega. So a of omega is equal to a of minus omega, and b of omega is equal to minus b of minus omega. So if both complex numbers are equal, their real and imaginary parts must be equal as well. So this is the consequence of this fact. So it tells you that the real part is actually even. So can you see that the real part is even? So a omega is equal a minus omega. So real part is even, and imaginary part is actually odd. So you can write this as well. So what about this observation? The third bullet, x of omega and x of minus omega had the same magnitude. So of course, if you have two signals which are related with this, x of omega is equal to x conjugate of minus omega. If this is the case, of course, norm of x of omega is equal to norm of x conjugate of minus omega, and is equal to norm of x of minus omega. Conjugation does not change the norm, so there's a minus here, by the way. Conjugation does not change the norm, so x conjugate of minus omega and x of minus omega have the same norm. Well, what about the angles? The angle of x of omega is nothing but tangent inverse b of omega over a of omega, and angle of x of minus omega is nothing but tangent inverse b of minus omega over a of minus omega, of course. And this is equal to, well, I know that b is an odd signal and a is an even signal, so it is equal to minus tangent inverse b of omega over a of omega. So it's equal to minus angle of x of omega. So this is due to the fact that b is an odd signal, a is an even signal, odd over even is an odd signal. So I can take this minus out since I have an odd signal with a minus sign. So the angle of this signal for the angle for this real x of t, the Fourier transform of real x of t is calculated with these formulas. the even part is the real part is odd, real part is even, imaginary part is odd, and phase is odd, and magnitude is even. So if I have both real and even signal x of t, so instead of realness, what happens if it is odd? In this case, x of omega is real and even as well. So it is easy to show x of omega is x of minus omega. This is equal to x conjugate of minus omega. The first term tells you that it is even, and this tells you that it is real. So in this case, x of omega is equal to x conjugate of omega. So it is real and even. Well, if x of t is both real and odd, in this case, x of omega is purely imaginary and odd. So it is like this: x of omega is equal to x conjugate of minus omega. This is equal to minus x of minus omega. So this tells you that it is odd actually. Those two telling you that it is odd, but this is telling you that it is purely imaginary. Well, you can show it like this. So x of omega is nothing but j a of omega. So x conjugate of omega is minus j, let's say, of omega. X conjugate of minus omega is minus j a minus omega. And these are telling you that if x of t is both real and odd, in this case, x of omega is purely imaginary and it is an odd signal. So, well, any signal x of t, well, remember this from very beginning. Any signal x of any real signal x of t can be uniquely written as sum of its even and odd parts. So I can write x of t as x even of t plus x odd of t. Well, x even of t has Fourier transform of real x of omega, and x odd of t has Fourier transform of j imaginary x of omega. So this is your exercise, quite easy. Well, you know how to write x even of t. X even of t is, x of t plus x of minus t over 2. So you know this very well. So by using this property, you can show this and the other as well. So in the next exercise, I will use this property. Remember our x of t, which is e to the power minus, well, actually there is an error here, minus a times absolute t. I think you remember this example. It was looking like this. So this is t, this is 0, this is x of t, this is 1. So I will try to find the Fourier transform of this signal. First, I will start with my e to the power minus at ut. I know the Fourier transform of this very well. It is 1 over a plus j omega, remember. If I find the even parts of this signal, what is this? E to the power minus at ut plus e to the power at u minus t over 2, and it's equal to 1 over 2 times e to the power minus a absolute of t, and this is 1 over 2 x of t. So the even part of e to the power minus at ut turns out to be half of my x of t. Well, by using this property, I know that even part of e to the power minus at ut has the Fourier transform of real part of 1 over a plus j omega. This is due to the fact that e to the power minus at ut has Fourier transform 1 over a plus j omega. So this is nothing but a over a squared plus omega squared. So the even part of e to the power minus at ut has a Fourier transform of real of 1 over a plus j omega, and it is a over a squared plus omega squared. So finally, x of t is nothing but 2 times even part of e to the power minus at ut, and this is equal to 2a over a squared plus omega squared. Well, you can find the Fourier transform by using the previous discussion that we have done already, but you can, by just a simple observation, this x of t is nothing but 2 times the even part of e to the power minus at ut. I know the Fourier transform of e to the power minus at ut is 1 over a plus j omega, and its real part is this. Simply 2 times of this is my Fourier transform. So this is just you know, a basic example for the properties of real and even signals. The next property is the differentiation property. If you derive a signal in time, the Fourier transform signal is multiplied with j omega, and if you integrate a signal in time, the Fourier transform signal is multiplied with 1 over j omega, so just the reciprocal of this one, plus some term. But actually this term is nothing but the DC term or the average term that may result from integration. Well, I will not deal with the proof of this, so if you are interested, please go and check the book, but just know that derivation means multiplication by j omega in Fourier domain. Integration means division by j omega in frequency domain plus some DC terms. Well, I will prove the first one. If you start by writing x of t as the synthesis equation from minus infinity to plus infinity, x of omega e to the power j omega t d omega. If you derive d by dt x of t is nothing but 1 over 2 pi integral. So this term does not depend on time. The only term that depends on time is this exponential. So j omega is the if you derive this, it is j omega times e to the power j omega t. So I have j omega here, x of omega e to the power j omega t d omega. So if you compare, j omega x omega is the Fourier transform of d by dt xt. Here I have a note. If a0 is negative, if a0 is 0, sorry, if a0 is 0, the integration from minus infinity to t, actually there's the integration from minus infinity to t, x tilde tau d tau is finite. So how can you check this? What is a0? A0 is nothing but 1 over t0 within a period, let's say t0, x of tau d tau. Let's write here a conjugate. So this is the average over one period. So if this is non-zero, it means that this integral is infinite. So if my signal has zero average within a period, then this integral is actually finite. The next example tells you how to use this derivation property. Remember those linear constant coefficient differential equations. I have d by dt yt plus alpha yt is equal to x of t. So what is the impulse response? Remember, homogeneous and particular solutions, and you know, if x of t is impulse, then I have y of t as the impulse response. So we had some boundary conditions. I'm sure you remember them well. Well, instead of this, I will use the differentiation property to find the impulse response. First, I will take the Fourier transform of this relationship. So d by dt yt has Fourier transform j omega y omega plus alpha times y omega is equal to x of omega. So that's it. So if let's say if x of omega is 1, it means that x of t is delta t, then my y omega is of course the impulse response. So if x of t as the impulse of t at the input, then at the output I have y of t, which is h of t, the impulse response, and y of omega is nothing but the impulse response of my LTI system. So this tells me that j omega times h of omega plus alpha times h of omega is nothing but x of omega, and h of omega is actually 1 over alpha plus j omega. Well, I know that h of t is e to the power minus alpha t ut. So I know that these are the Fourier transform pairs. So that's it. By the way, also I used that delta t has Fourier transform of 1. So this is simply the usage of their differentiation property to find the impulse response for a constant coefficient linear differential equation. The next example tells me to find the Fourier transform of a linear ramp signal. So what's the linear ramp signal? This is my linear ramp signal. Let's say that it is in the interval from -1 to +1. So this is my ramp signal. So this is 1, this is -1. Actually, this is y equals t in the interval -1 to +1. So what is the Fourier transform of this one? Well, first I will define x of t as dyt by dt. So x of t is defined as the derivative of y of t. What is this? If I derivate this ramp signal, the derivative is constant in the -1 +1 interval, but there is a jump here, right? You see the signal is 0, then suddenly it is -1, it is +1, then it is suddenly 0. So there is a jump in those regions, so it means that I have impulse. So it is sum of two signals. In the first one, I have this this rectangular signal pulse, which is 1. Then I have sum of impulses. Okay. Again, the area of, so this is impulse minus t minus 1. This is impulse minus impulse t plus 1. So I have two impulses with amplitude -1, or the area -1, if I derivate y of t. So the signal is constant. It is decreasing suddenly. It is let's say 1 here, and it is decreasing suddenly. So there are negative impulses at those areas. So the derivative of this linear ramp, which is confined in the region from -1 to +1, is nothing but sum of a rectangular pulse plus two impulses. Well, I know that this rect t, so this is nothing but, by the way, rect t over 2. So this is rect t over 2. So I know that rect t has Fourier transform sinc omega over 2 pi. Rect t over 2 has, by using the scaling property, has Fourier transform 2 times sinc omega over pi. And I know that impulse of t has Fourier transform of 1. and impulse of t minus 1 has Fourier transform of e to the power minus j omega, and impulse of t plus 1 has Fourier transform of e to the power j omega. So I will use all of them to find the Fourier transform of x of t, and then I will find y of t. Let me continue from there. So x of t has Fourier transform x of omega, which is 2 times sinh omega over pi minus e to the power minus j omega minus e to the power j omega. These minuses are actually from those minuses. I mean. So I'm almost finished. What about y of t? Y of t has Fourier transform of x of omega over j omega plus pi x of 0 impulse of omega. So what is this? It is simply 2 times sine omega over pi minus 2 cosine omega over j omega plus 0. This 0 is actually pi x of 0 impulse of 0. X of 0 is actually 0 because what is x of 0? You can check from here. Sinh 0 is 1, right? Sinh 0 is, so this is 2, this is 1, this is 1. So 2 minus 1 is actually 0, which is x of 0. So I can find the Fourier transform of y of t by using the Fourier transform of x of t and using the integration property. Well, this is not, some cumbersome operations, but you can try to find the Fourier transform by directly using the analysis equation and the y of t formula as well, but you should use, integration by parts and other calculus stuff, or you can use the integration property by yourself. So it's your choice. So the next example is the Fourier transform of unit step. So it is simple. I know that delta t is nothing but dut by dt. So ut is nothing but integral of delta t. So delta t has Fourier transform of 1. So this is, let's say, h of omega. Ut has Fourier transform of h of omega over j omega plus pi h of 0 delta omega. So there's omega here, by the way. So this is nothing but 1 over j omega plus pi impulse of omega. So this is the Fourier transform of my unit step signal. So that's it. So some basic, relationships governing differentiation and integration. The next property is the duality property. This duality property tells me that if I have the Fourier transform pair x of t and x of omega, I can, if I switch t and omega, let's say, indices, I can find the Fourier transform of x of t as 2 pi x of minus omega. Well, this is actually an interesting property, and its proof is, again, requires some calculus. So let's start with writing this, let's say, fu. Let's define it as integral gv e to the power minus j u v dv. So if I change variables of, let's say, u equals omega, v equals t, in that case I have f of omega in the left hand side, which is equal to integral g of t. Instead of v, I will put t e to the power minus j omega t dt. So what does it tell you? It tells you that gt and f omega are Fourier transform pairs. So because this is actually the actual synthesis equation, analysis equation. So f omega is equal to integral gt e to the power minus j omega t tells you that gt and f omega are Fourier transform pairs. Well, starting from this now, I will tell you that let's u equals t and v equals minus omega. If you do this, in the left-hand side, now you have f of t, which is integral from plus infinity to minus infinity now, because there's a minus here, e to the power j omega t minus d omega. This is nothing but 2 pi times 1 over 2 pi integral from minus infinity to plus infinity g of minus omega e to the power j omega t d omega. So this again tells you that f of t and 2 pi g minus omega are Fourier transform pairs. In the right hand side, so this is the actual synthesis equation with g minus omega. Instead of g omega, now I have g minus omega in the integration, and there is 2 pi here. So ft and 2 pi g minus omega are Fourier transform pairs. So this is the end of proof. If gt and f omega are Fourier transform pair, so are ft and 2 pi g minus omega. I have here an interesting example. Let's try to find the Fourier transform for 1 over 1 plus t squared. Well, I know that e to the power minus alpha absolute t has Fourier transform of 2 alpha over alpha squared plus omega squared. So this is my x of t. This is my x of omega, capital X of course. So if let's say if alpha equals 1, so let's write x of t for alpha equals 1. This is nothing but 2 over 1 plus t squared, and this is the Fourier transform of 2 pi of x of minus omega, which is 2 pi e to the power magnitude omega. So it tells you that 2 over 1 plus t squared and 2 pi e to the power minus omega are Fourier transform pairs. So what do I have? If I write my actual term, 1 plus 1 plus t squared, 1 over 1 plus t squared is the Fourier transform of pi e to the power minus absolute omega. So this is the case. By using the duality property, I have proved this. The next thing is rectangular and Ceng signals, but you can check this by yourself. So by using the duality property, use the if you have Ceng t, what is this? So by using the duality property, please try at home that find the Fourier transform of this Ceng of t signal. Well, I will finish. We are almost done. I want to finish today the lecture, so today the property. So I will continue for 20 more minutes. The next property is the Parseval's relationship. It tells you that if you can find the total energy of your signal by integrating the signal in time or its Fourier transform. So this left-hand side is the total energy of a signal. I can calculate this by integrating the absolute t squared in time, or I can find this by dividing by 2 pi and integrating x of omega norm squared. So this is the Parseval's relationship. Again, it is easy to, let's say, derivate. Let's start with writing this norm square dt. This is nothing but x of t times x conjugate of t dt. This is equal to integral x of t 1 over 2 pi integral x conjugate of omega e to power minus j omega t d omega dt. So this is actually x conjugate of t. Well, I'm sure you are following that the x's with omega are capital X, so Fourier transforms. So again, if I change the positions of the integrals, this is x conjugate of omega 1 over 2 pi integral x of t e to power minus j omega t d omega. Of course, this is nothing but x of omega, so it's equal to 1 over 2 pi integral norm of x of omega squared d omega. So this is the end of proof. In the left hand side I have this relationship, and in the right hand side I have this term. So it tells me that the Parseval's relationship is actually valid as expected. Well, the next example asks me to calculate compute some values. The first one is actually there are two signals. This is the first signal, the second signal. I'm asked to calculate this E and D for those signals. What is E? E is integral from minus infinity to plus infinity norm of x of t squared, and D is the derivative of the signal evaluated at t equals 0. So I will start with E. What does E tells me? Integral from minus infinity to plus infinity norm of x of t squared dt. By using Parseval's relationship, this is nothing but integral from minus infinity to plus infinity norm of x of omega squared d omega. So what is it? It is 1 over 2 pi integral from minus 1 to 1 over 2 pi d omega plus integral from minus 1 over 2 to 1 over 2 pi over 2 d omega plus integral from 1 over 2 to 1 pi d omega. Well, actually, this is nothing but, by the way, there is a square root here. It's not visible in your notes. There are square roots here. Okay, so if you evaluate this, this is nothing but 5 over 8. So the next is D. D is defined as dxt by dt. Let's tell that this is nothing but y of t. Then y of omega is actually j omega x of omega. And y0 is 1 over 2 pi integral from minus infinity to plus infinity y of omega d omega. So it is 1 over 2 pi integral from minus infinity to plus infinity j omega x of omega d omega. Well, this is y0, and y0 means actually d x of t by dt evaluates that t equals 0, and j omega is actually an odd signal, right? This is an odd signal. X of omega here is an even signal. If you multiply an odd signal and an even signal and integrate, so this is nothing but 0. So this was for the first signal. For the second signal, please try this at home as the homework. So this is your homework that you should try at home. Convolution property. Well, actually, this property is quite important. We will use this in next term, in next year. If you go and take digital image processing course, actually we will be dealing with those convolutions. It tells you that if you convolve in two signals in time, they are multiplied in frequency. So this is the convolution property. So actually the proof is quite simple. Let's again start with y of t, which is x of t convolved with h of t. This is equal to from minus infinity to plus infinity h of tau x of t minus tau d tau, and this is from minus infinity to plus infinity h of tau 1 over 2 pi integral x of omega e to the power j omega t minus tau d tau. Actually, this is nothing but x of t minus tau. I've used the synthesis equation, so I know that x of t is 1 over 2 pi integral x of omega e to the power j omega t d tau. Instead of t, I put t minus tau. So that's simple. If I change the positions of the integral, so I have 1 over 2 pi integral from minus infinity to plus infinity x of omega, and integral from minus infinity to plus infinity h of tau e to the power minus j omega tau d tau e to the power j omega t d omega. Well, I have here e to the power j omega t times e to the power minus j omega tau. So e to the power minus j omega tau is here, e to the power j omega t is here. So what is this? This is nothing but h of omega. So this is equal to 1 over 2 pi integral from minus infinity to plus infinity x of omega times h of omega times e to the power j omega t d omega. Well, this is y of omega, and if y of t is x of t convolved with h of t, y of omega is x of omega multiplied with h of omega. So that's quite easy. So you should try this by yourself as well, but it is just simple properties of integration and some change of variables. Here I have an example. Let's say I have an LTI system which is defined with h of t is equal to t minus t0, and find its frequency response h of omega, and the output Fourier transform in terms of the Fourier transform of the inputs. So that's simple. H of t is, it is simple. So let me go back and open this. Okay, it's simple. If I have h of t, this is the Fourier transform of h of omega, and this is equal to 1 times e to the power minus j omega t0. So if you have y of omega, which is equal to h of omega times x of omega, this is nothing but x of omega times e to the power minus j omega t0. So what about x of t? X of t is simply equal to, sorry, y of t is simply x of t minus t0. So that's it. Y of t is the shifted version of my input x of t. The next is the differentiator system. Differentiator is an LTI system, and what's its impulse response? If x of t is at the input, at the output I have y of t, which is dx of t by dt, and y of omega is nothing but j omega times x of omega, which is equal to h of omega times x of omega, and of course h of omega is simply j omega, which is the frequency response of my system. Well, the next example is similar. I have h of t, which is the impulse response of an LTI system, and it is e to the power minus at ut, and I have x of t, which is given as e to the power minus bt. Both a and b are positive numbers, and what is the output in frequency and time domains? So first I will start with writing the convolution. So x of t is e to the power minus bt ut, and yt is simply x of t convolved with e to the power minus at ut. Well, I know that x of omega by heart, it is 1 over b plus j omega, and h of omega is simply 1 over a plus j omega, and y omega is simply multiplication of h of omega and x of omega. It is equal to 1 over a plus j omega times b plus j omega. So this is the Fourier transform of my y of omega. So that's simple. In order to find y of t, I will use partial fractional expansion. So if a is not equal to b, then y of omega is something like this, 1 over a plus j omega times 1 over b plus j omega. It's equal to a over a plus j omega plus b over b plus j omega. I will not solve for this partial fractional expansion, but I know that you know it very well from calculus classes. A is simply 1 over b minus a, b is simply minus 1 over b minus a. So if I put everything into 1 over b minus a parentheses, I have 1 over a plus j omega plus minus 1 over b plus j omega. Well, I know that this is the Fourier transform of e to the power minus at ut. I know that this is the Fourier transform of e to the power minus bt ut. So I have y of t is equal to 1 over b minus a e to the power minus at minus e to the power minus bt ut. So this is my y of t. Well, what if a is equal to b? In this case, y of omega is simply 1 over a plus j omega squared. Okay. Well, I know that e to the power minus at ut has Fourier transform of 1 over a plus j omega. What about t times e to the power minus at ut? This has the Fourier transform of j d by d omega 1 over a plus j omega, and this is nothing but 1 over a plus j omega squared. So t e to the power minus at ut and 1 over a plus j omega squared are Fourier transform pairs. So that's it. So this is the actually result of frequency differentiation property. Well, next example tells me about those frequency selective filters. We will have much more examples or much more cases again in Ceng 441 in digital image processing lecture. This is what does an ideal low pass filter looks like. So it is, let's say this is omega c, this is minus omega c, so it is 1. So this is my ideal low pass filter. It is 1 for omega in the interval minus omega c to plus omega c. So this is the stop band. This is the stop band again, and this is the pass band region. So the signal passes only the frequency components within this interval, and it completely rejects the others. So x of t and y of t is, related with the impulse response. So if I have x of t at the inputs, and if h of t is my impulse response, I have y of t at the outputs. Of course, this is equal to h of t convolved with x of t. What about y of omega? You know, y of omega is x of omega multiplied with h of omega. So if you have such an x of omega, let's say this is my x of omega, and let's say this is minus omega c, this is plus omega c. If you filter this with h of omega, and remember h of omega was given here, it was only passing the plus minus omega c region. Then at the output you have y of omega as this. So this is omega, this is omega c, this is minus omega c, this is my y of omega. So at the output only this selected region passing at the output. So if you filter an image with a low pass filter, actually the image is blurred. It is becoming flu. Details are lost. So this is the main, let's say, idea of filtering. Here you have an exercise. Please try this exercise as homework. It is simple. You have this signal, Ceng type signal, and it is filtered with an ideal low pass filter. So you know that Ceng has Fourier transform of rect. So the rectangular signal is filtered with, again, a rectangular low pass filter. So the last property is the modulation property. If you multiply two signals in time, they are multiplied in, if you multiply two signals in time, they are convolved in frequency. So you can prove this by using the duality property. So I will not mention about the proof, but it is just simple. My example tells me that I have m of t times e to power j omega 0 t. So what is x of omega in terms of the spectrum of m of t? Well, you know that by using the frequency shift method, if you shift in frequency, you are multiplying with a complex exponential in time. So method 1 tells me that actually using the frequency shift method, x of omega is nothing but m of omega minus omega 0, where m of t has Fourier transform of m of omega. Well, with second method, I will use the modulation property. So x of omega is equal to 1 over 2 pi m of omega convolved with, let's say, h of omega. And here h of omega is nothing but the Fourier transform of e to the power j omega 0 t. So it is equal to 1 over 2 pi m of omega convolved with 2 pi impulse omega minus omega 0. And this impulse omega, 2 pi impulse omega minus omega 0 is the Fourier transform of this e to the power j omega 0 t. It is simply 2 pi's cancel out, convolving with a complex exponential shift signal. So this is equal to m of omega minus omega 0. So this is my second method to calculate. My next example tells you to find the spectrum of r of t, which is multiplication of s of t times p of t, and p of t is nothing but a cosine signal. Again, I can write r of omega directly. R of omega is simply equal to s of omega convolved with p of omega. This is equal to 1 over 2 pi. Sorry, there is 2 pi here. This is equal to 1 over 2 pi s of omega convolved with pi impulse omega minus omega 0 plus pi impulse omega plus omega 0. And this is nothing but the Fourier transform of my cosine omega 0 t. So this is equal to 1 over 2 s of omega minus omega 0 plus s of omega plus omega 0. So multiplying with cosine simply shifts the spectrum to the left and right and divides by 2. So this is the effect of multiplying with a cosine term. The next example is actually similar. I have two signals. So what are they? I have x of t, which is obtained by multiplying sine t over pi times pi over t over pi times pi times sine t over 2 pi times pi over t over 2 pi times pi 2 pi times pi times 1 over 2 pi. This is nothing but 1 over 2 pi times sinc t over pi times sinc t over 2 pi. So I have my x of t, which is obtained by multiplying two sinc signals. Well, the Fourier transform of sinc is rect, so two rectangular signals are convolved in frequency. So the rest is your homework, but remember, multiplying in frequency in time domain means convolving in frequency domain. So my rectangular signals are convolved in frequency. Actually, we will not cover the rest, so the rest is not covered. So this is not covered as well. So again, the demodulation. So these are telecommunications related issues. So we will not cover them. So these are for these are not actually needed for computer engineering guys. So let me stop recording.